Wayne. Okay, so let me select my phone here and share it. And then I'll read number 44 why that's connecting here. But it says a clock with a brass pendulum. Okay, so a clock with a brass pendulum has a period of exactly 1 second, or 1.000 seconds, at 20 degrees Celsius. If the temperature increases to 30 degrees Celsius, how much does the period change? And then B, how much time does the clock gain or lose in a week? So the part that is review, and this is what I call the review question, is the period of a pendulum is 2 pi over the length of the pendulum divided by G. At least a simple pendulum. Physical pendulum got a little more complicated, and it depended on how it was shaped. But I think for this one, since we don't have a shape to work with, we'll just say it's a brass simple pendulum. And of course, this calculates out, and this is the point, to be a period of exactly 1 second. And then from that, we can get its length. And so if I grab my calculator here and take exactly 1 and divide it by a 2 and divide that by a pi, square that, and multiply that by G, we're looking at a length of 0.24, and I better do quite a few decimal places here, 82 meters. Okay, because then here's where this chapter comes into play. It's going to warm up, and warming up means it's going to be a little bit longer. And this is where we're going to have to switch over to the textbook here and find the linear expansion coefficient for brass. I'm hunting here for it. There's brass. And so this is a 19 times 10 to the minus 6 inverse degrees Celsius. Its length is 2482. And back to the problem, I think they said it warmed up to 30, not warmed by 30, right? So it's at 20 and it increases to 30. So that means the change in temperature is going to be 10 degrees. So there's not much of an increase, but there is a little bit. Let's see, 19 times 10 to the minus 6 times 10 times the original length. And so this is going to be a 4.965 times 10 to the minus 5. So if I take that increased length and add to it 0.248, actually, you know what I'll do? I'll go and grab the original length. I'll use all 10 decimal places. Because it's not going to change the first 4, but it's the next one out. So the 2482, it was 2482.36. Now it's 2482.84. So it's not much of a length increase, 0.248284. You don't see it till you get to the 5th decimal place. However, that is going to make a slightly longer period. So I will put in this new length and see what the period comes out to be. So taking that new length and dividing it by 9.8, taking the square roots of all of that, and then multiplying it by 2 pi. It looks like I get 1 point. How many zeros is that? 1, 2, 3, 4 zeros. And then I'll just go 9, 5. So, yeah, certainly not much of an increase. And if you're only talking about 1 or 2 periods, you're never going to notice this longer period. But it accumulates every second. And so at the end of a long period of time, and that's what it says, how much time does the clock gain or lose after a week? So it's not much per second, but after a week, it might be noticeable. Let me scan the answer here, see if I even got that part right here. Yeah, the author says 9.50 times 10 to the minus 5. 1, 2, 3, 4, 5. Yeah. So not much there. So you might then do part B this way and say, okay, it is then going to be slower. So in other words, it's a little longer, so it's taking a little bit longer. In other words, one swing would take this much. It wouldn't take a whole second. So in 1 second's worth of time, it has fallen short by this many seconds per, and this is going to look weird, it fell behind by this many seconds in 1 second.
Oh, I see. So it's like,
So I'm losing this much of a second every second.
so if you like saw the clock, it's just so small that you probably wouldn't notice it. But if you took like a slow motion camera, you might see that it's slightly behind a little bit.
Right. And it's this much in a second. So if you multiply it by 60, it's going to be that much behind in a minute. And if you do that again, it's going to be that much behind in an hour. And if you multiply that by 24, it's going to be that much behind in a day. And now, if you multiply it by 7, you're going to be that much behind in a week. So seconds, minutes, hours, day. And you're going to be left with how many seconds is it behind in 1 week? All right. So 9.5 times 10 to the negative 5. How many seconds in 1 second it's behind? Times 60, that's how many minutes. Times 60, that's how much it's behind in an hour. Times 24, how much it's behind in a day. And so times 7. So it looks like we're about 57 seconds, maybe 57 and a half seconds after a full week. So about a minute. So not a big deal. 10 degrees warmer in this particular scenario.
You still miss a minute worth of swings in a week, though.
Yeah. So it is gonna run slow. I've heard stories that this for your really big old-fashioned grandfather ones that are much longer than this, because this is only 1/4 of a meter. But they're a meter long or more. So the effect is 4 times. So in a week, it's 4 minutes behind. But and the stories I've heard are friends of my folks who they're snowbird. They call them snowbirds because their main house is like in Michigan, and then they go out during the winter. So this time of the year, they're in Arizona, and so they just closed up their house and leave for 4 months. But if you lose, 4 minutes a week for 4 months, it's very noticeable when they get home and the clock is way behind and it's real cold in the house. I mean, it's ahead because it got cold, not hot. But and it's probably even colder than 10 degrees Celsius, so it's, I've heard them say it's like, yeah, it's like hours ahead by the time they get back home after spending all winter in Arizona.
Interesting. Thank you.
Sweet. All right, I'll switch back over here. All right. Well, let's move on to another one. All right, Hunter's got one for me, it looks like here. All right. So, chapter 20, number 21. And looks like we're at 325 right now. Okay. Let me switch back over to the questions and scroll into chapter 20, number 21. Oh, good. We're getting a PV diagram. So, yeah, these are really important and it'll take a little while to digest. So I'm glad you guys are starting to get to the point to ask about these. I have a feeling you'll be asking a lot more of them next Friday. But the PV diagrams are powerful tools. And I kind of explain that think of a PD diagram as kind of being the fundamental thing you want to look at, sort of like when we did Physics 121, we had that free body diagram. And so we're like, okay, always look at that free body diagram. It kind of helps you understand the problem a little bit better, help you get to the answer. And that's what PV diagrams do here. So in this case, let's see what they're asking, because there's a lot of value in a PV diagram. So not one particular problem is going to show you all the advantages of the PV diagram here. But here it says a sample of an ideal gas is expanded to twice its original volume of 1. So in the PV diagram, they make it very clear that your V is on the horizontal axis and you're at 1 cubic meter, and we're going to expand it to some new volume of 2 cubic meters. And the pressure then is going to go from some initial pressure, and they show a little pattern that it takes. And that's where the diagram comes useful, because the shape of the pattern or the shape of the line from one volume to another is different depending on how you expand the gas. And so we're going to come across these different names. And I think near the end of this chapter, you get 3 of the 4 common ones, but there's almost an infinite number of different ways you can warm up the gas or expand the gas. Anyways, and so how you expand it, and so we have names like expanding it at constant pressure, which we call isobaric. Now, that would just be a straight line on a PV diagram because the same pressure. So that's probably one of the easiest ones to think about on a PV diagram. But we could have constant pressure, we could have constant volume, we could have constant temperature, we could have constant energy, or what we call adiabatic. Those are the 4 big ones. But anyways, this one is not one of the what I call the famous 4, but they do say in the diagram here that the pressure changes by some equation where I guess alpha, and I think they're going to explain alpha in just a second, times the volume squared. So to me, making a graph of y equals some constant x squared would be a parabola. So not a surprise they drew a picture that looks like a parabola. So they're showing me a nice little graph of a parabola here. All right. So go back to the reading. It says in a quasi-static process where, so they give me the equation in the reading. Okay, so there it is. Where alpha is 5 in units of atmosphere and meters to the 6th power, which makes sense because when you put in volume in cubic meters, so this graph is volume in cubic meters, and you square it, you'd get meters to the 6th, and so you're going to get pressure in units of atmosphere. So I do want to keep a close eye on my units here because it depends what they ask. See it right here. They say how much work is done. All right. Now, going back to physics 121, we said work is force integrated over some distance. And I'll keep it simple. I'll just say the force in a particular direction, like x, as it is expanded or moved in the x direction, you integrate that, that's going to be the work. Now, the reason I am going to put that here is because if I make kind of a container that's in the shape of a cylinder that maybe I'll just say has a piston, since we did a couple of problems earlier with a piston. Okay. The pressure and the force from the gas on the piston is pushing upward. They say that fancy word quasi-state because what they're saying then is, maybe there's a balance roughly in pressure pushing down from the outside world. So the weight of the piston and the atmosphere, and the problem we did last also had a little dog sitting on top of it. And here's what I'm getting at. If we're talking about the work on the gas, we want to look at the force then, and maybe I should put force from the outside of the gas, dx. But they make this little step by putting a minus sign and saying this is going to be roughly to the force from the gas itself, inside of the gas. Okay. And those forces are roughly equal and opposite if they're in kind of a quasi state here. I'm saying that because I wanted to justify where the negative sign comes from. Because the force on the inside is actually the pressure of the gas itself times the area that the gas incorporates times the distance up. And that right there, the area and the distance it moves up, let's say dx, is the change in volume. And I'm sure the author wants you to start the problem right there, but I thought I would just throw that in there for your background. You'll see it when you do the reading and you do the lectures, but how do you calculate the work done on the gas here? And so that's what we're asked. How much work is done on the expanding gas? So I need that formula. Okay. So going on to page 2, I'm just going to say the work is negative the integral of the pressure and how the volume changed.
I think you froze up again.
So, oh, it sure did. Oh, you know what I think? Let me just check. Okay, let's do a stop share, then a reshare. If I don't do that, it doesn't usually connect. Okay, so let's try that. Ah, now it found the laptop. That's good. Spin that around. All right. So while that's connecting up, so I was trying to say here that all that other work probably isn't necessary in terms of doing the homework, but I thought it'd be a good review. But now I think you can see how this is. If you think of this as your PV diagram, this is the y-axis, P, and this is your x-axis. So when you integrate a function, they're saying really the integral of that function is the work being done. So if we go back to page 1, a nice visual representation then, using our information from our calculus class, is the area under the curve. And so sometimes visualizing the area under the curve can help. I don't know if I need it for this problem because I actually have an equation. So I'm just going to integrate the equation. I'm not actually going to bother to look at the area under the curve. But there are some problems where looking at the PV diagram and keeping in mind then that the area under the curve is the work done. So that's what's another nice thing about PV diagram. So in this case, I'm going to put a negative, and I'm going to put in the equation. Let's see. What was that equation? It was right here. It was 5 atmospheres over cubic or meters to the 6th power times volume squared. And then we can integrate that with respect to volume. And of course, that is a fairly easy integral to do. I'll pull the 5 atmospheres over meters to the 6th out in front of the integral. And then I just have an integral of v squared dv. Well, that's just v cubed over 3 evaluated from the initial volume to the final volume. And I could have put the limits here, but it was from 1 to 2. 1 to 2, or in this case, 1 to 2. And I didn't convert atmospheres to pascals already. Perhaps I should have. I was debating that. I saw that and I go, I really don't like working with atmospheres, especially when they start asking about energy. But I was just going to leave it there until I needed to change it. Now I need to change it. But this would then be 1/3, and it would be 2 cubed minus 1 cubed. So volume cubed. So 2 cubed minus 1 cubed. And again, I should be careful here with my units. Let me just put the 5 and the 1/3 over here. But again, this is atmospheres per meter to the 6th. Because this 2 cubed is 8 minus 1 cubed, that's a 1. 8 minus 1 is 7. And I need to point out that this is in volumes of cubic meter, which has now been cubed. So this would be meters to the 9th power. So again, let me just put my numbers together. So the 7 and the 5 make 35 over 3. And then again, I have my atmospheres, and I have meters to the 6th and meters to the 9th, which then reduces down to cubic meters. And that's really kind of my clue to convert this to pascals, because a pascal, which a pascal is a Newton per square meter, multiplied by a cubic meter would give you a Newton times a meter, which is a joule. So that's our kind of our normal units for energy. I guess technically you could say an atmosphere times a cubic meter is some new unit of energy. We can give it a name, I suppose. But I think we really should be putting this in units of joules. So let me switch this to 101,300 pascals, where it says atmosphere. And that way, when I take a pascal and multiply it by a cubic meter, I'm going to get the answer that in the units that I'm accustomed to for energy in joules. So that's why I told you on the other review sessions here today that it's nice to probably have pressure in pascals, because there's going to be a lot of questions about energy. And that's exactly what you need, is energy in joules most of the time. Otherwise, we'd be in some kind of weird units that aren't common, something called an atmosphere cubic meter. And I suppose somebody somewhere uses it, but
kind of weird.
Yeah, certainly not a standard. Okay, so let me go the 35 divided by 3, and then times the 101,300. And I still got the negative sign. 1.18 times 10 to the 1, 2, 3, 4, 5, 6. So 1.18 million joules. And let me make a comment about the negative sign. Actually, yeah, especially let me make a comment about the negative sign. Because here's where I want to give a warning to you and anybody else listening to this. The way that survey deals with the work energy is the opposite in sign that the way the OpenStax deals with it. Here's how survey does it. Survey says if any energy is going into the object, give it a positive. If any energy is coming out, give it a negative. So energy in is a positive, energies out are a negative. Okay? So if you look at this negative, here's what it would tell me. This negative would tell me that energy is coming out. And that makes sense. The gas is expanding. The energy is actually leaving the gas. If we come back to this kind of picture, the gas pushes it upward, and it's leaving the gas and it's giving it to whatever it's lifting up. So if I just use this object as a dog again to match what we did earlier, I would say that energy is coming out of the gas, and now the dog is gaining the energy. The dog has been given some potential energy. The dog has been lifted up higher and high. So the dog gained energy. So the dog's energy is positive, but the energy came from the gas. So the gas should be losing energy. So anytime a gas expands, it's pushing on something. It's giving energy to it. So an expanding gas should always have a negative on its energy. It should be losing some of its energy. Okay, so I like that. And the fact that it comes out negative is consistent with that. Now, let me give you a warning for those of you who are using the open stacks, it is kind of customary, but weird to do this. If heat energy goes in, it's positive. But if work energy goes in, it's negative. Whoa.
That's kind of weird.
Okay, and that's why it's kind of weird. You're not consistent, right? However, here is the advantage. Here's why some people and some authors like this approach. Is most of the time when we actually build something practical, like an internal combustion engine, we put heat in, positive, and make the gas expand and do work on a piston, which turns the tires, which makes the car go. So we like to give the positive sign to the things we want to happen. We want heat to go in, work to come out. And the positive sign is for the good stuff. If heat comes out, that's a negative.
Is that like a consistent thing? Some people just approach it differently, or
Yeah.
That's a little confusing for sure.
Yeah, well, here and here's where it really gets confusing then. So if you look in the OpenStax book, this equation that I just derived for you right here with the negative, they would have said, let's define it the other way around so you won't see the negative in front. So I probably need to give you guys warning because you might be looking at it and go, whoa, 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 how come I have a negative and the answer doesn't have a negative? So remember, if you're doing the homework, you're doing it from Survey, and Survey's got a little definition. Here's another thing that drives me crazy with that definition from OpenStax. If you do something like this, so you have a little container with a gas in it, and you ask this question, well, what is the total energy in this box? Or maybe I should say the change in energy. So it already has some energy, but then let's say I go to change it. I may do work on it, or I may give it heat, or I may do both. But if you have the same definition that energy going in is positive, then these, have the same sign. If I were to give it energy by work, so I squeeze it, okay, and if I were to give it energy by heating it, both of those are positive until the total energy has increased by the sum of the two. But if you use the OpenStax definition and you call work going in negative, then you have negative work plus Q is equal to the change of the total energy. Now, they usually write it as Q minus W. But to me, that's really hard to see conservation of energy. And to me, that does not look like I'm adding two energies together. Hey, I lost you. I lost my whole phone.
Yeah, I couldn't tell if you were still writing or not at a certain point.
Yeah, I thought you were just like explaining things. I didn't realize you were writing stuff.
You know what happened?
Forget to charge it or something?
Oh, okay. Well, it says it's overheating. So it said shut off due to excess heat.
Yeah, the cameras will do that to it.
That and having Bluetooth connected at the same time for hours on end.
Yeah, but here's what's different than in the past. See, in the past, it does get warm on me, So while we're working, I've always noticed it gets warm, but it's never overheated. But I've always wondered if it was about to, because it is warm. And so like on the breaks, I shut it off. Last session,
Mhm.
I don't know if you noticed, but when I was hooking up the phone, I forgot to plug in my power cord. I usually just leave it powered up. But for some reason I forgot, okay? And so the whole last session, the whole hour and a half, the battery was draining. Now I didn't notice it, but when we were done, I go, oh, I forgot to charge it. I forgot to plug it in. And I looked at the battery and it was down to 30%. And I go, well, no big, it lasted. So I'll just, when I plug it in again. Well, okay, so now here's what's different. Now, besides using the camera and the Bluetooth, I was actually also charging a low battery.
Mm.
And as I hold it in my hand right now, it's really warm.
Mhm.
So that's what was new. It was, in the past, I've always left it charged in, and I start the morning at 100% charge because I always charge it overnight. So it's just been doing the camera and the Bluetooth, but hasn't really been charging the battery. Maybe a trickle charge, but not really charging. But this time I had a low battery. So I wonder, let's see, I'll check this out. It got it up to 65%.
Yeah, it always sucks when you overheat though. My screen got like burned one time because and
Keep blowing on it.
yeah, from overheating.
But let's just do this. I'll with 65%, I think I can just run it on battery and it won't overheat. Yeah.
Yeah, if you want to take a second too on the phone, like I also don't want you to break your hardware.
Oh.
Yeah.
Yeah, I get that. I don't think that's
One of my old phones actually, like, the battery was getting like it was well overdue for an upgrade.
yeah.
And so like the battery was just like getting really old. And this was back in high school, my senior year. And like I was walking to a friend's house because we actually had a physics project. It was the project where you drop an egg from the top of a stadium so that it doesn't break. So we were like, we were meeting at her house to like go figure out how to build the device. And like I was just walking and felt my pocket get really warm, and I pulled out my phone and like the battery started, you could see it kind of burning through the screen. So I like threw it on the rocks really fast, and it kind of like it just killed itself. And I was like, okay, cool. No phone, I guess.
Yeah, that was a problem. Was it one Samsung had that problem really bad? Was that a Samsung?
Yeah,
No, it was an iPhone.
It was an iPhone.
It was just really like it was way overdue for an upgrade.
Yeah, I haven't had that with my phone, but I did one time. I think I've even mentioned this one time before, because I think I told you guys this story in 122, but I had a 9-volt battery that I put in my pocket with change. And the 9-volt batteries, they have the two terminals right at the top. And so it short circuited on some coin, and the battery was just rapidly discharging. And all of a sudden my pocket just got blistering hot. I was like, ow, what's going on? Reach in and pulled out the battery, and tossed it onto the ground. And then I got to thinking about it. I said, oh, it must have been short circuiting because of the change in my pocket.
Were there like, was the change hot too?
I think so. Yeah, that's a good question. I don't know if I remember, but I think I remember a quarter was really hot. So I think it must have, got on the edge of a quarter. Yeah. Yeah, because you're, straight 9 volts with very little resistance.
Yeah, kind of scary. Don't want to get burned.
Yeah. Well, and then that Yeah, I've seen ones. Mostly they were those vaping, lithium vaping ones that, somebody's standing around, and oftentimes it's like video surveillance at a liquor store, and they're in the store, and all of a sudden a battery just short circuits because it's not built with good quality, and the pocket catches on fire. So I must have seen a dozen YouTube videos like that.
I need to look those up.
Yeah. If you got some time, look those up. They just
they'll turn them into like little rockets. It's crazy.
yeah. So if it got a good quality, and then like this one here, obviously it recognized the too hot and it shut itself down. Now, okay, so before I lost my phone signal there, I was trying to say this: be very, very careful for you guys looking, because normally there's only a little bit of difference between the Survey and the OpenStax, but this is a significant different one. It's why I tried to give a warning to you guys in the last Sunday's weekly address. I said, be careful. It probably didn't mean anything to you until you actually come across it. But if you call the energy going in positive and energy coming out negative for both heat and work, they have the same sign. And so you just add them together for the total energy. You just say, hey, the total energy is the sum of the two. But if you define heat energy as positive going in, but work energy is positive going out, I mean, stuff going in is negative. You need the negative of the negative to get the total energy on the inside. And so this is, I think, somewhere where where I lost my phone signal is, I was going to say, if you are in the OpenStax book, you'll see something like this. The change in total energy is, and they go Q minus W. And they'll say something like, you just add the energies together. And you look at that and you go, wait, that's not adding the energies together. That's subtracting the energy. But you're really doing this. You're really saying, take the Q and add the absolute value of the work.
Oh, Mike, it happened again.
Well, that's just I hope, a regular freeze. Let's see if I can feel the warmth. Yeah, it doesn't feel real warm or anything, so. But I think that's my normal lose contact for some reason.
I always feel so bad for my electronics nowadays because, like, I mean, it's not like you're in a classroom taking notes. You're using your computer to watch videos while look at notes, and like, just feel bad because it feels like everything's working so hard just to keep up.
Mm-hmm. You're running everything into the ground to make sure you get everything done. like 12 hours in the day, and I'm like, oof, it doesn't break on me.
Yeah, like my fan on my laptop is like constantly at the high speed, just trying to cool everything off.
Yeah, and I probably do this to myself too, because maybe this is part of my problem. And then I've got all this work going on, so I've got a bunch of tabs open up, and I go, okay, well, I don't want to shut it all the way down. I want those tabs there, so I just let it go to sleep, and then I open it up, and it doesn't get a chance to reboot, and then all those little errors kind of accumulate. But bummer, the thing is just spinning again here. Well, why it's spinning? Looks like it connected. I'm gonna take off my hoodie. It looks like it's afternoon has come.
Starting to get into warmer weather, like.
Yeah, it's a lot warmer today than I thought it was going to be. But the way my little room is situated is it's on the west side, so I always start the morning really quote cold. And then about this time in the afternoon, that sun just warms up the west wall. And anyways, I just it gets real warm in here. Okay, so where it froze was right here. So I was trying to say, be careful here on the OpenStax book of their definition of work, because when you talk about the increase in energy, you're really talking about the heat added plus the absolute value of the work. And that looks a little funny, but to give OpenStax credit, Surway's actually going to do the same thing in chapter 22. He's going to start just doing absolute values because, again, there's something nice about saying when the gas expands and loses energy. So when you burn gasoline in your car and it expands, calling that a positive work, even though it's leaving the gas, is kind of nice, because that means it's going to your car. It's making your car's engine work. And then that engine is doing other things like making it go fast, or running the air conditioner, or running the generator, which makes electricity, which runs the radio, So it is nice to work with absolute values. And even Surway is going to do that real soon. So there's certainly a case could be made that maybe OpenStax is doing it better because they're actually just getting into it right now instead of holding off. I don't know, but I do want to start giving you guys some warning that
I
could.
usually use the Survey book, so.
Yeah, I have the OpenStax, but I end up using the Survey myself too. I prefer the way it's organized.
Mm-hmm. I bought last semester, I bought the volume 2 of OpenStax, and I mean I want to collect the other 2 volumes just as reference later on in life, but I figured the homework's out of the survey, everything's still kind of out of the survey. It's just nice having everything in one, especially for this class, everything in one book rather than having to flip through 3 different books.
Yeah. Good.
Do they still update the survey, or is that they just kind of done making those?
Well, no. They're still there. They're actually, it's a really good book. A couple of years ago, we kind of decided, for better or worse, because I do think the Survey is a little better book than the OpenStax. But the OpenStax started, I'll say, when it first started, it wasn't that good, but it got better and better. And the idea of the OpenStax is that it was going to be a free book forever. And free books in the past have been of low quality. So they actually, it's put out by Rice College, and they got a huge amount of donations. The biggest one comes from the Bill and Melinda Gates Educational Foundation. Mm-hmm. And that one, it actually became a really good book at that point. And so we were kind of at a interesting spot on, okay, do we continue with an expensive book? Mm-hmm. Or do we go with this new one coming out? And I decided that maybe we should go with the free one. I mean, there's a lot to be said in a free book. Yeah. But not if it's a crappy book. And anyways, ultimately we said, let's just kind of phase it out. And so I guess I'm going down that road. I thought I would have phased it out by now, but the OpenStax, they did a really good job of writing the book. So it has really been improved. I think learning from it's pretty good, but I don't think their problems are as strong as Caliper. So that's why I've said, well, let's just stay with the problems from the old survey book. We have a license for that one, and we got all the materials, and we'll just kind of work on both of them. And at first, well, this happened also about the same time where I think you guys know this, that, I used to do the whole series, 121, 122, and 123. And starting last spring, so this would be the third semester, I haven't done 121. But Doug did 121 last spring for the first time, and I think
we were
Daniel,
both
were
in
you there?
Doug's class.
Yeah, I took him there. Yeah.
Okay, yeah. Okay, so you were both okay. And then but he was a fan of the OpenStax one. And but he was also a fan of making his own problems too. So the problems didn't bother him.
He
but-
didn't start doing the different problems until the next semester when Hunter and I were still in his class. He still used the survey problems.
Okay.
Yeah.
Okay.
I don't know if he ended up switching it to like how he did for 102, but I took him 102 that previous fall, and he had his own like online system that authenticated problems after you typed them in and stuff. But
Yeah, I think
and
he
that
did.
that's what he likes, and that's where he was headed to. So in your semester being his first one, he just used the problems I used to give, but he only did that for you guys. Then last semester and also this semester, he's kind of making his own. And my phone is overheated again here, so I'm blowing on it, going, okay, what should I do here?
no, if at least for me, if we need to wrap up early, that's totally cool. Thanks for making the time on your holiday.
Yeah,
Oh,
thank
yeah.
you. And I mean, we got through a lot of problems today.
Okay.
Yeah, and we covered a lot of good like conceptual topics that were really good for helping me straighten that out.
Okay.
Mhm.
Well, then I'll say, if you guys don't mind, since my phone's not working, although I could switch over to my whiteboard, but I'll just say,
That's
all right,
good.
shoot me a question, and once my phone cools down and I'll start making videos again.
I've been doing physics all day, so I think a break is
Time for a break.
kind of needed.
Yeah, I'm gonna switch to math in a second, but then I'll
Okay.
take it. Awesome. Well, thanks so much. Have a good weekend.
Okay. All right. Bye, guys.
Yeah, the way I do my weeks are usually like on like work